Okay, section 15.5 has to do with what we call ice tables. Which are a really versatile way to find concentrations that are involved in equilibrium reactions. And so we'll introduce what those letters I, C, E mean in the context of this reaction right here. H2 gas plus I, 2 gas is in equilibrium with 2HI. And that is a gas. Okay, and we have a, let's see. And so we have the reactants and the products here. We need to make sure that the reaction is balanced, so we've got the coefficients there. And when you encounter a problem with equilibrium, we need to consider 3 stages of the reaction. So I stands for initial. Those are the initial amounts of all of the species present before any reaction occurs. And then C is the change, how much the reaction proceeds, how many moles or how much pressure in atmosphere or how much concentration and molarity is going to change for each of these 3 species. And then finally, E is the equilibrium values. And the idea is you set up this table here. I'll make it look nice with lines kind of separating everything. You'll set up this table here, and these equilibrium values, whatever they may be, should fit into an equilibrium expression. KEQ is equal to the concentrations of products over concentrations of reactants. And we can then use that equilibrium expression to solve for unknown variables. And I'm talking kind of vaguely because we're going to look at a variety of different ways to use ice tables. One great thing about our equilibrium expressions is that they can actually be used with a variety of different units. If I have, for this, for example, we're going to have a Kc is equal to concentration of Hi squared over the concentration of H2 divided by the concentration of I2. So for this we could use pressure. You could use a Kp value and relate that to Kc because Kp is equal to Kc times RT raised to the value of delta N. Or you could use the molar concentrations, or we could kind of recognize that each of these concentrations is moles divided by volume. And so if I wanted, I could say this is moles of Hi divided by the volume squared, and moles of H2 divided by the volume, and moles of I2 divided by the volume. And in some cases, you'll find that the volumes will cancel out. Those are the cases where you could use moles directly. And if we're looking at Kp, well, the pressure is always proportional to the number of moles. And so for Kp's, we can always use N, or the number of moles, instead of the pressures, if for some reason that is more convenient. So we should be careful with Kc values. If delta N does not equal 0, then we're going to have to use concentrations instead of moles. And anyway, I'm going to go ahead and use concentrations for this next problem, so I'll erase all of this. All right, so the question is, If we take 5, we are going to use moles in this particular problem. Okay, so if I take 5 moles of H2 and 5 moles of I2 and put them in a reaction chamber and let them reach equilibrium, then we can observe that the HI concentration is 0.900 moles. Okay, so if I give you a question like that, and you can see this question in the notes PDF that I provided on Canvas. So we have 5 moles of H2 and oops, a mistake here, and 0.5 moles of I2 are reacted in a 1 liter chamber, and at equilibrium we observe that the HI concentration is 0.9 molar. Then, because it's a 1 liter chamber, I'm backtracking again. I was on the right track in the first place. We're going to do concentrations. Because it's a 1 liter chamber, that 5 mole and 0.5 mole can be expressed as molar amounts, because we're just dividing by 1 liter. And then our final concentration of HI is 0.9 molar. Sorry, it's been a few months since I worked this particular problem, and I'm obviously struggling a little bit to set it up. But the important thing is to, at the beginning of the problem, recognize where we need to be putting each of the values. So the initial conditions was 5 moles of H2 in 1 liter chamber and 0.5 moles of I2 in a 1 liter chamber. I didn't explicitly say it, but we'll assume that we had 0 moles of HI. And now looking at the stoichiometry of this, then we can talk about the amount of change in these values using a variable x. So I don't know how much things have changed yet, but I know that the stoichiometry says that we'll lose equal amounts of H2 and I2, and that we'll gain 2 times that amount of HI. That's what our stoichiometry of 1 to 1 to 2 says. And then our final amount here then is going to be 5 molar minus X and 0.5 molar minus X. And this 0.9 molar here, that is 0 plus 2x. In other words, the initial plus the change is going to be your equilibrium amount in each of these columns. Now this is a problem where it's pretty straightforward how we solve for x here. We can use the equilibrium amount of HI to know that x is equal to 0.45 molar, right? If our final concentration is 0.9, then 0.9 equals 2x, x is 0.45 molar. And so we can now calculate these molar concentrations. 0.5 minus 0.45 is 0.05 molar. And 5 minus 0.45 is going to be 4.55 molar. Now we've got actual values for our equilibrium concentrations, and we can place them into our equilibrium expression. 0.4, oh no, sorry, that's wrong. We have 0.900 molar concentration of HI. We'll square that. And 4.55 molar for the hydrogen, and 0.05 molar for the iodine. And let's just plug those numbers in and see what we get. 0.9, oops. There we go. 0.9 squared. The 2 stars there are how we square things in my weird calculator here. And we'll divide that by 4.55, and we'll divide that by 0.05. And what I get is not what I expected. My notes just might be wrong. Let's make sure we haven't done anything wrong here. We'll do 0.9 times 0.9 divided by, we've got 5 minus 0.45 and divided by 0.5 minus 0.45. Maybe some of the stuff I did in my head was wrong. Nope, okay, looks like my answer key is just wrong. It should be 3.56. This is an embarrassing start, but I'm going to just go ahead and continue with the lecture, and you get to laugh at my mistakes here. Oops, what was it again? 3.56 equals 3.56. And that actually does not match the value from our quiz the other day. So actually I'm guessing my problem is right here in this equilibrium concentration. I actually calculated it ahead of time so that I could put a realistic value here. And anyway, I apparently messed up badly. But as far as the numbers that you're given here, this solution is consistent, and it taught you the method well enough. So I'm going to just leave it behind and keep going. Okay, so this is a relatively simple way to use an ICE table, and they get to be more complicated from here. Alright, so let's consider this reaction. Carbon monoxide gas plus H2O gas. This is going to be in equilibrium with H2 gas plus CO2 gas. And we'll go ahead and make our ICE table. And we can write down the equilibrium expression down here. We have a value for Kc. That is equal to 5.80. And that ought to equal the concentration of hydrogen times the concentration of carbon dioxide over the concentration of carbon monoxide and the concentration of water vapor. There we go. We've got all of the sort of skeletal structure to this problem. Now we're supposed to find the equilibrium conditions if the initial concentrations of carbon monoxide and water are both 0.0125 molar. 0.0125 molar. And we have no product. Now in this case, we'll again talk about the change in terms of some unknown variable x. We'll lose some amount of these. We're not sure exactly how much. And then we'll gain an equal amount of each of these. Well, the carbon dioxide equilibrium concentration is 0 plus x. That means it's just x. Hydrogen, 0 plus x is just x. And then water would be 0.0125 minus x. And 0.0125 minus x. Now we don't have any easy way to solve for x here because we didn't actually give you a measured concentration for any of these final amounts. But we do have the equilibrium expression. We know that 5.80 is equal to the concentration of H2 times the concentration of CO2. That's x times x. And we know that it's divided by the concentration of carbon monoxide, 0.0125 minus x. And the concentration of water, 0.0125 minus x. And here we can see an equation with only one unknown, it's x. And if we look at this, it's going to be some sort of a quadratic equation. We have x squared terms that are present. We would have to FOIL out all of the parts down here in the denominator, and it could become quite difficult from an algebra perspective. But in all of these problems, we're going to do our best to make assumptions or mathematical simplifications so that we don't have to actually resort to using the quadratic formula. In this case, we can look at it and rewrite this right side as x squared over 0.0125 minus x squared. And we can take the square root of both sides now. Because both the numerator and the denominator are squared, we could rewrite this as that whole quantity squared. And if we take the square root of 5.80, and the square root of the right side, what we end up with is square root of 5.80 is equal to just x over 0.0125 minus x. We managed to get rid of all the squares, and that is a very substantial simplification of the algebra required to solve this. Okay, so let me do some erasing here. I'm obviously running out of board space, and we don't need this portion of the ice table anymore. I'll leave up the E for just a moment. And let's just now solve that. So we'll have square root of 5.80 times 0.0125x minus the square root of 5.80 times x is equal to x. So I've just taken this denominator and brought it over and distributed the root 5.8 over to both sides. And we can go ahead and add the 5.80 times x to both sides, plus the square root of 5.80x to that side. And what we'll end up with is the square root 5.80 times 0. This never should have had an x. It's 0.0125 minus x, so it's square root of 5.80 times 0.0125. And we'll pull out the x here, so we end up with 1 plus the square root of 5.80 times x. Okay, and finally we can solve for x now. It's just going to be this product divided by that sum. So I'm going to have hold on, let me see if I have square root defined. I don't. Okay. So the square root of 5.80 times 0.0125 divided by 1 plus the square root of 5.80. And I get a value of x equal to 0.00883. 0.00883. All right, so now let's now that we have the value for x, we can return to our equilibrium conditions, and we can begin to put actual concentrations in here. That would be 0.00883 molar for the hydrogen gas. 0.00883 molar for the carbon dioxide. Then what's 0.0125 minus x? 0.0125 minus 0.00883. Looks like that's 0.00367. 0.00367 molar here, and 0.00367 molar there. We have our equilibrium concentrations. And if we like, we can go back and kind of double check this. Does the equilibrium expression equal 5.80 as it should? So we'll take 0.00883, that's the concentration of hydrogen, times 0.00883, concentration of carbon dioxide, divided by 0.00367, that's the concentration of carbon monoxide, divided by 0.00367 again. 367, the concentration of hydrogen. And look, it's 5.78 to within 2 sig figs, then that is correct. I'm actually surprised it's off by that far, but the error is small in the 3rd sig fig, and so I guess I should have carried an extra figure in the value of x if I wanted it to really come out perfectly. Okay. So just to sort of summarize, in that problem, we were able to avoid using the quadratic formula because we could take the square root of both sides, because the numerator and the denominator of the equilibrium expression were both squared values. And you know, that wasn't quite the crazy coincidence that you might at first think. If you start with equal amounts of reactant, and if your reaction is sort of symmetrical, losing one and gaining one of all of your reactants and products with no change in the number of moles and things, then that'll work out. It's not totally uncommon to run into problems like that. But it is definitely a special case. So let's look at this reaction instead. I have I2 gas in equilibrium with 2 I gas. And this is going to have a Kp value at 1000 Kelvin. Not that that matters, but we're at 1000 Kelvin here. Has a Kp value equal to 0.260. And so what that means is that 0.260 is going to equal the pressure of iodine atoms squared divided by the pressure of iodine molecules. Okay, now we'll do an ice table, ICE, and let's look at the conditions that we have here. It says find the equilibrium conditions if a reaction chamber is initially charged with 0.2 atmospheres of iodine atoms and 0.005 atmospheres of I2. Okay, now we have now both reactant and product present under initial conditions. And so it's not really clear which way this reaction will shift in order to reach equilibrium. So let's first of all calculate our reaction quotient. That would be 0.2 squared over 0.00500. Let's figure out what our reaction quotient is. 0.2 times 0.2 divided by 0.005. And I get a reaction quotient of 8. Q is equal to 8, which is much larger than our K value. That means we have too much product, and so our change is going to be negative 2x and plus x here. See that? We've got a stoichiometric coefficient of 2 and 1, so it'll be 2x and x, and because it's shifting toward reactants, this will be negative 2x, and this will be a positive x. So what we get is 0.200 minus 2x, and here we get a 0.00500 plus x. And we can go ahead and plug this in now to the equilibrium expression. 0.260 is going to equal 0.200 minus 2x squared over 0.00500 plus x. And now we have an equilibrium expression that we cannot easily take the square root of both sides. Sure, that would get rid of the square in the numerator, but now we've introduced an even worse problem by putting a square root of x in the bottom. Now there are two different ways to solve this. I'll go ahead and erase everything up here, and we'll show you the long way to solve this. And the long way is to apply the quadratic formula, which says that if you get an equation in the form of ax squared plus bx plus c is equal to 0, if you can get an equation into that form, then you know that x is going to equal negative b plus or minus the square root of b squared minus 4ac all over 2a. That is the quadratic formula. My hat's off to whoever discovered and proved that that is the solution. That is the solution for every equation that you can get into this form. And so our goal is to just manipulate all of this algebra until we can get it looking like this form. So let's first take our denominator and multiply it over to the left side, and distribute that 0.260 through. So 0.26 times 0.005, that's going to equal 0.0013. So we have 0.0013 plus 0.26x, and that is going to equal 0.200 minus 2x squared. Okay, is that fair for a first step? And now let's square the right side, and we'll have to FOIL this, which is a term for how you square a binomial like this. I'm not going to go into that. If you need to learn how to square a binomial, I'm sure you can find some videos on YouTube or something. But we'll end up with the same thing on the left side, 0.013 plus 0.26x. And then we'll have 0.2 squared, which is going to be 0.04. And then we will have 0.2 times a negative 2, so that is a negative 0.4x. And then we'll go the other way, we'll have the negative 2x times the 0.2, so we'll have another negative 0.4x. And then finally, negative 2x times negative 2x is plus 4x squared. And I see that that is just barely running off of the frame, but that is a plus 4x squared. And we can simplify this 0.0013 plus 0.26x is equal to 0.04. We can combine those, negative 0.8x plus 4x squared. Oh, that's fantastic. Now we can move both of these over to the right side to get us in the proper form for the quadratic formula. So what's the squared term? We have 4x squared. And then we're going to have 0.26x we'll subtract from both sides. So negative 0.8x minus 0.26x is going to be a negative 1.06x. And then we've got a 0.04, and we will be subtracting from that 0.0013. And so we're going to get a plus 0.0387. That is equal to 0. Let me double check that real quick. 0.04 minus 0.0013, 0.0387. And now we have our values for A, B, and C. And so x is going to equal a negative b. Now b is already a negative, and so that would be a positive 1.06. Plus or minus, and we'll show you how to deal with that in a minute, but basically we'll just do the plus first and see if we get an answer that makes sense. And then we'll do a minus and see if we get an answer that makes sense. Okay, plus or minus the square root of b squared, so that would be 1.06 squared, minus 4 times a is 4, and c is 0.0387. And all of this is going to be over 2 times a, which is 4. What a wonderful mess we have here. Let's run these numbers. So we have actually I'm going to kind of put parentheses here, because in the end we're going to be divided by 8. 2 times 4 is going to be 8. Okay, so I have 1.06. Oops. 1.06 plus the square root. So here's my square root function. I'm going to have the square root of 1.06 squared minus 4 times 0.0387. And I get a value of x here that is 0.2212. So x is equal to 0.2213 if we round that up, because it's 27. And let's back out of the calculator for a second here and talk about whether this number makes sense. Well, our concentration of iodine atoms is 0.2 minus 2 times x. And, 2x is going to be more iodine atoms than we have. We'd end up with a negative pressure. And negative pressures are nonsensical. They don't make any sense in the physical world. So that is a solution that we can throw away. Now I'm going to do the exact same calculation here, but you can see I'm going to subtract that square root instead. Now I get a number, x is equal to 0.04372. Okay, now that number at least makes physical sense as a possibility, 0.04372. So our equilibrium concentration of iodine atoms would be 0.2 minus 2 times that. So we'll say 0.2 minus 2 times, and I'll just reference that solution. It's going to be 0.11255. 0.11255. Sorry, that's a pressure in atmospheres. And our pressure for iodine molecules is 0.005 plus the value of x. Oops, there we are. So 0.005 plus 0.04372 is going to be 0.04872. Okay. Let me clear this out, and you can see now our equilibrium pressures. Let's put them into our equilibrium expression and just double check that they equal 0.260. They sure ought to, because I don't want to start this whole video over again. We'll have 0.1125. We'll square it. That's the pressure of iodine atoms squared, divided by 0.04872, the pressure of iodine molecules, and it equals 0.25977, or 0.260 when rounded to 3 sig figs, which is great. Math works. The quadratic formula worked. Now, I hope that you are impressed at the fact that these are very difficult. I don't mean impressed with me for solving it, but I hope I have given you the impression that solving the quadratic formula is tedious, because we as chemists are really interested in practical results. There's always some amount of error to our measurements. And there's no point in finding a precise mathematical value when we have a certain amount of uncertainty based on our measurements in the first place. And so we like to come up with tricks and tools to simplify our life. After all of that, you're going to love what happens next. I'm going to erase all of this, really. Okay. If we return to this expression right here, I notice that I have a relatively big number, and I'm subtracting 2x from here, and I've got a relatively small number, and I'm adding x to it. And all of our troubles as far as having x squared came from the numerator here. What if I just say, hey, I'm a sloppy chemist. I know that the value of x is, or I suspect that the value of x is going to be very small. So what if I just say 2x is much less than 0.2? What's a mathematical consequence of that? Well, that's that 0.200 is going to be pretty close to 0.200 minus 2x. And so, since these are close to each other, why don't I just ignore the 2x in that numerator and say that it's 0.2? What if I simplify this whole equation to say 0.260 is equal to 0.200 squared over 0.00500 plus x. Now that would make things a whole lot easier because 0.2 squared is a mathematical operation so simple I can do it in my head. That's going to be 0.04. And now we just have a simple equation with one x in it. So let's solve for x now. We've already done this, but I forgot. What is what is 0.005 times 0.26? So we're going to end up with a much simpler formula here. 0.0013 plus 0.260x is equal to 0.04. And so I'll subtract 0.0013 from both sides. And I get 0.260x is equal to 0.0387. And I'll divide both of these by 0.260 divided by 0.260. And I end up with x is equal to 0.0387 divided by 0.260. And I end up with x what have I done? -0.04 minus 0.0013. It's 0.0387 divided by 0.26. Oh, sorry. This has gone wrong in exactly the right way. I apologize. So we'll go back to the 0.0387 divided by 0.26, and I get x is equal to 0.148, and this 0.148 as a value for x is nonsensical in the context of the 0.200 minus 2x. That would give us a negative value again. And I apologize, I gave you a false setup because in this case, that assumption that we made here has given us a nonsensical answer. In fact, 2x is not small compared to 0.2. We can see that that assumption has led to a very, it has led to a logically inconsistent result. And so this substitution was not justified and a bad idea. And the whole point of this problem is to show that sometimes you cannot simplify the equation at all, and you have to bite the bullet and do the quadratic formula like I've done. Okay, now we're finally going to get to a good one where we can do a simplification. And I apologize. I always look over these notes, which I actually just wrote last year, and so they're not totally old notes. I always look over them before I do these videos, but this time I obviously missed the key points when I looked over these. I said, oh, we're going to do this problem and that problem and that problem, and I failed to see what the key point of each of those problems was. The problem we just did was meant to illustrate that sometimes you cannot avoid doing the quadratic formula. This next one, you can avoid the quadratic formula through clever simplifications. Okay, so if we consider acetic acid reacting with water, that's going to produce H3O plus aqueous. Oh, that's not acetic acid. I apologize. That is formic acid. HCOO minus aqueous. Formic acid reacting with water to produce hydronium ion and formate ion. We can do an ice table here. We'll set this up in preparation for giving us real values. And water is a liquid. It doesn't actually appear in the equilibrium expression, so I'm going to just kind of draw the line showing our formic acid, hydronium, and formate ion columns, and just make it clear that we don't care about the concentration of water. Indeed, we don't ever calculate it or know it, because water is a pure liquid solvent in this case. It won't show up. And our Kc is 1.8 times 10 to the negative 4. I'm pretty sure that will work. Okay, and that is going to equal H3O plus times HCO2 minus over HCO2H. Those are the aqueous species in this reaction. Okay, so if I start with 0.25 molar formic acid, and we'll say 0 and 0 for those. What are going to be my equilibrium concentrations? We'll say negative x plus x plus x, and we get x, and 0.250 minus x. This gives us x squared over 0.250 minus x. And if we make the assumption that, let me just go ahead and erase the top part of our ice table so that we can reclaim some of this board space. And if we make the assumption that x is much less than 0.250, then 0.250 minus x is pretty much equal to 0.250. And that'll simplify things a lot. We can say 1.8 times 10 to the negative fourth is equal to x squared over 0.250. And now we can just multiply that over to the other side. So the 1.8 is going to become 1.8 times 10 to the negative fourth times 0.25 is going to be 4.5 times 10 to the negative fifth, I believe. Let's double check that, because I've not had a great track record today. 1.8 e negative 4 times 0.25, 4.5 e negative 5. And that is now equal to x squared. And we can just take the square root. And we get x is equal to np.sqrt, that's our square root function, 4.5 e negative 5. And we get 0.0067. 0.0067. Okay, well, that number clearly doesn't violate our physical constraints in the same way that the last one did. 0.250 minus 0.0067 is not a negative number. So this is a reasonable value. But we can be a lot more precise in defining whether our assumption here was valid or not. Let's look at this equation here. We had 0.250 minus x, and we said that x is small enough to ignore in this expression. Now we've calculated the value of x, and the question that we want to ask is x less than or equal to 5% of 0.250? So is it at most 5%? Is it 5% or smaller than the value that we subtracted it from? If so, then this assumption was good. We can take this number and run with it. And the purist mathematicians will say, but technically you're wrong. But the chemist inside of us says we only get 3 sig figs anyway. This is good enough. And I'm getting hungry for lunch, so we're just going to take this and go with it. If x is greater than 5% of the value that you subtracted it from, then you're going to have to say, oh, I wish I could use this value, but it turns out that our assumption was probably not well justified. And so let's figure out what that is. 0.0067 divided by 0.25 times 100%, and it looks like it was about 2.68%. So it is below that 5% threshold, and if we only get 3 sig figs, then that's good enough. 5% is your magic number. Now, now that we have our value of x, we can replace things here. We know that our formate ion concentration will be 0.0067. We know that our hydronium ion concentration is going to be 0.0067. We could go on to find what the pH is going to be. And then let's just quickly do this last calculation 0.25 minus 0.0067. And I guess we really should round that up. If we want 3 sig figs, it should be 671. So I'll just throw those ones on there. And I'll make sure that I subtract the 671 here. That's going to be 0.243. So that's going to be 0.243 molar. And I want to draw particular attention to the fact that earlier in the stage of this process, we said that 0.250 minus x is about 0.250. We ignored the x. Well, that was good enough for finding the value of x. But now that we know the value of x, we no longer have to make that assumption at this stage. We'll take the 0.250 and we'll actually subtract that value of x, and we get 0.243 molar. That is the concentration. Okay, I apologize that this lecture was a bit frazzled. That was entirely not my intent. I don't think I'll go refilm it because we're going to be using ice tables a lot, and I think you know, over the course of the next couple of weeks, you're going to see these same steps taken over and over and over again. In fact, I'm about to record the quiz where we'll do these steps again, and I think that you'll get the message. Even if today was a little bit difficult, you will definitely see all of this again and again and again. Dealing with ice tables in different various scenarios is going to be a central skill to the next couple of chapters of the textbook. So I hope that you are able to really understand how to construct the ice table. Where do I put the values that I know from the context of the question? How can I tell what the change will be, what the equilibrium values will be? How do I fit them together into the equilibrium expression? And can I make reasonable simplifications to that problem in order to avoid the arduous task of solving the quadratic formula? Okay, good luck.